Okay, welcome back. Let's look at implementing this Henderson-Hasselbalch equation a little more deeply and how we can use it to solve the pH of a buffer. So this equation is derived from the Ka expression. Right? So that's where it's coming from, and I'll show that in a second. And it allows us to calculate the pH of the buffer by knowing the pKa, or the Ka, right? And the initial concentrations of our weak acid and our conjugate base ion. Now, this equation is really a shortcut, if you will, and it's a shortcut that works as long as that x small approximation is valid. Now, as we've seen, as we've gone through the acid-base chapter, we've seen, almost all of the problems that we see with these acid-base, these weak acid, weak base equilibriums, we've been able to make that approximation. So almost all the time, we can use this Henderson-Hasselbalch equation as an alternative to doing those ice tables in these particular types of applications, right? In situations where we have both the acid and its conjugate base, or the base and its conjugate acid present in solution. Now, I hesitate to dive into this too deeply, but I sometimes think it's important to sort of understand a little bit about the math and to understand that we don't just throw these equations around. So if we start off with our acid ionization equilibrium, and we set up our Ka expression, and we specifically solve for hydronium ion concentration. So we have this solution that says hydronium equals the Ka times the ratio of Ha over A minus. Okay. So we had to do a little bit of arranging, right, to get here, but this is what we end up with here. Okay? So if we go from there, and we take the log of both sides. Now, remembering that if we have the log of two things multiplied by each other, we can separate them out. And then we multiply by -1. We can end up with the following equation, right? We can get the negative log of hydronium ion concentration on the left-hand side, and the negative log of Ka. Now, it would be plus, right, the log of the ratio of A minus over Ha. Now, before we start looking at here, we notice the ratio flipped, and that has to do with keeping the signs in line here, right? So again, this is what we started with. We took the negative log of both sides. If I take the negative log of two things multiplied by each other, they can separate out. Now, if I have the negative log of this ratio, I can flip the ratio, and this becomes, right? If I flip this ratio, then this becomes a positive. So that's how we end up with this equation in particular. Now, this page number is incorrect. For the book, I believe it is page 792 in the current edition. So hopefully it should be somewhere close to that in your e-textbook, but it's going to be in the section on buffers 18.2 in the chapter. Okay, so now we have this equation. So now it's kind of sort of tying these things together, right? If I have the negative log of hydronium, right, that's the pH. If I have the negative log of the Ka, that becomes pKa. And we now have the pH equals the pKa plus the log of the concentration of our conjugate base over our acid. Now, again, this page number is incorrect for this version of the textbook. So this becomes our Henderson-Hasselbalch equation. And again, we just started with our simple equilibrium expression, and we can convert it into this equation that allows us to find the pH based on the Ka of the acid that we're dealing with as the pKa, if we know the concentrations of our conjugate base and our acid to start with. So now the question becomes, is this a situation where I can use the Henderson-Hasselbalch equation, which is going to be a lot shorter, or do I have to do the full ice table for, this particular scenario? Now, again, this is only going to be appropriate if we are in a situation where we have concentrations of both the acid and the conjugate base. So the two places where we see that are either a buffer solution or the start of a titration before the equivalence point, right? Because again, we are essentially creating a buffer solution while we're doing that, right? Because we're creating the conjugate base as we neutralize the acid. So it's not like you're going to put this into any sort of calculation, right? So the calculations that we did in chapter 17, right? You're not going to substitute the Henderson-Hasselbalch, in there, right? But when we can use it, right, is when the X is small approximation is valid. Now, again, typically this means that you have, initial acid concentrations are fairly large, and Ka is fairly small. So it's that idea of having 2 to 3 orders of magnitude between the equilibrium constant and the initial concentration. So that's why we get that 100 to 1,000 times larger than the Ka value. So some of the calculations that we're going to do, and I'm going to post a video of the calculation specifically after this one, but we're going to want to calculate the new pH after adding acid or base, right? Now, in order to do this kind of problem, so we have one problem which is just calculating the pH of a buffer, and we'll talk about how we'll do an example of doing that as well. But what about after we make these additions, right? Can I calculate what the pH of this buffer is after I add some base or some acid, right? Well, of course we can. But we have to do 2 problems. The first problem is a stoichiometry problem. So we have to figure out how the moles or concentration, however we want to think about it, how the moles of our, let's say we're starting with a weak acid, how the moles of that weak acid have changed based on the, let's say, base that we added, right? So we got to figure out how the concentration of HA and A- has shifted after adding this acid or base impurity. And so we've seen that if we add acid, we're going to react it with the conjugate base, and so the conjugate base is going to go down, the HA is going to go up, so we're going to shift. If we add base, the HA is going to go down, and the A- is going to go up. So we got to see what those values have become. So we have to do a stoichiometry problem based on how many moles that we've added, and so forth. Once we know that, then those can become, the new values here can become our initial concentrations in our equilibrium problem, and then we can solve an equilibrium calculation to get the pH. Now, this is where the Henderson-Hasselbalch equation comes into play, is in part 2. Now, just to give a little more graphical look here, if we start with the best kind of buffer, which has equal amounts of the two components. So graphically speaking, if I add acid, so I add a strong acid here, we get a downshifting of A minus and an increase in HA, right? If we add base, we get the opposite shift, right? And so we just need to see, well, how much has this shift been here, right? What is the difference here that we've created? And then that becomes our initial concentrations, and we can solve for the pH. Now, again, as I mentioned in the beginning, we tend to focus, in this book, as examples, we tend to focus on acid buffers because they tend to be more common. But, of course, we can make buffers using a base and a conjugate acid, and it's going to operate in the same way, right? It's just we're going to be working in a basic buffering range as opposed to an acidic buffering range. All right, so as I mentioned, as a follow-up to this video, I will be posting a video going through solving a problem or so, dealing with calculating the pH of buffered solutions.